Chapter 5, the definite integral 5.4, the fundamental theorem of calculus, part 2. Your objective for this lesson is still to evaluate integrals using the fundamental theorem of calculus. Okay, so in the first video we looked at fundamental theorem of calculus part 1. Now we're about to look at the second part of the fundamental theorem. And this says that if f is continuous at every point on the interval a comma b, and if f is any antiderivative of f on a comma b, then your integral from a to b of f of x dx equals big F of b minus big F of a. So when you're integrating, really you find the antiderivative and evaluate it at the endpoints. This is something that we've actually already looked at a little bit. It is also called the integral evaluation theorem. So you see, if I call it the integral evaluation theorem, it looks exactly the same. So, and just like it says, this is how you evaluate integrals. Yay! Okay. So example 5, evaluate the integral from -1 to 3 of x cubed plus 1 dx using an antiderivative. Okay, so the first thing that we need to do is to find the antiderivative of x cubed plus 1. So I know to find my antiderivative, I'm going to bump this up a power. So x cubed becomes x to the 4th. And I want to take my coefficient, right here, this is a 1, and divide that by this exponent. So I had a 1, I'm going to divide by this 4. Okay, so 1/4 x to the 4th plus, if I have a 1, that's x to the 0, so I'm going to have x to the 1st, or just x. And dividing the 1 that's right there by my not my coefficient, my exponent, I have 1/1. So really, this is just 1/4 x to the 4th plus x. Okay, so I can say that my integral, -1 to 3, of x cubed plus 1 dx is equal to this antiderivative, so 1/4 evaluated at 3 to the 4th plus 3, minus the same antiderivative valued at my lower bound, which is -1. Okay, so 3 to the 4th is 81, so I have 81/4, plus I'm going to rewrite this in fourths, so 3 is really 12/4, minus -1 to the 4th, well, that's an even power of -1, so I'm going to have a positive 1. So this gives me 1/4 minus 1 written in fourths is 4/4. So ultimately this is 93/4 minus -3/4. Minus negative is plus positive, so I have 96/4, which simplifies to 24. Okay, if we did this in the calculator, it would have been quite a bit faster to do, but again, remember, you're not always going to have the calculator on your AP exam, so you're going to go Math 9. Our function is x cubed, where's my cubed, Math 3, minus plus 1, comma x, comma -1, comma 3, close parentheses, and we get 24. So that way is a little bit faster if you're on the calculator active part of your test. Okay, example 6. Find the area of the region between the curve y equals 4 minus x squared, where x is between 0 and 3 and the x-axis. And for this problem, area means the total area, so no negative area under the x-axis. Everything's going to count as positive here. So why don't I go ahead and graph this, and I'm going to graph with the calculator just to save a little bit of time. So y equals 4 minus x squared. Okay, and we're going from 0 to 3, and so if I trace 3, I'm down here at -5. And it looks like I cross the axis at x equals 2. Yes, I do. Okay, so I'm going to use this to sketch a quick graph. So this is our graph. And I said we cross at x is 2. And at x is 3, I guess really this should be a little bit wider. At x is 3, we're at -5. So let me actually label the point. 3, -5, and this is 0, 4. Okay, so we need to find, oh gosh, the area between the curve and the x-axis. So that is this region here and this region right here. If I integrated from 0 to 3, the issue would be what I said before. This would be counted as negative area, and we wouldn't have the entire area. So what we're going to do is integrate twice, with our first region's upper bound being 2 and our second region's lower bound being 2. So let's integrate our first region first. So for the region 0, 2, we're going to have the integral from 0 to 2. We're integrating 4 minus x squared dx. So the antiderivative of this is going to be 4x, because we're going up a power, minus 1/3 x cubed. Okay, and we're integrating 0 to 2. Okay, so we're going to say 4 times 2 minus 1/3 2 cubed minus 4 times 0 minus 1/3 0 cubed. So this is 8 minus 2 cubed is also 8, but times 1/3 we have 8/3 minus 4 times 0 is 0, and this is also going to be 0, so minus 0. Okay, so we end up with 24/3 minus 8/3. That gives us 16/3 for our first region. Let's find the second region. So we're going from 2 to 3. So integrating from 2 to 3, the same function, so 4 minus x squared dx. So we're going to evaluate using the same antiderivative, 4x minus 1/3 x cubed from 2 to 3. Okay, so we get 4 times 3 minus 1/3 3 cubed minus 4 times 2 minus 1/3 2 cubed. Okay, so I already evaluated this at 2, and I found that that part was 16/3. So I'm just going to write that again right here. If you want to go through and do the whole thing a second time, go ahead, but I'm not doing it. So 4 times 3 is 12. minus 3 cubed is 27. 1/3 of 27, or 27 divided by 3, is 9. So I have 12 minus 9 minus 16/3, which gives me, this is 3. Let me write that in thirds though. So I have 9/3 minus 16/3. And this is negative 7/3. Okay, but I've already said I don't want a negative area. I want a positive area. So let me take this and take the absolute value, and that gives me 7/3. So now that I have one positive area and two positive areas, I can just add those together to get my entire area. So I'm going to say 16/3 plus 7/3, this is the total, equals 23/3. This is my answer. So my whole area is 23/3. Okay. So this is what we just did, a little summary. Finding area analytically. To find the area between the graph of y equals f of x and the x-axis over the interval a comma b analytically, the first thing you need to do is partition a comma b with the zeros of f. So you saw, we looked on the calculator, traced, and saw that we had a 0 at x equals 2. Second step, integrate f over each subinterval. So I broke this down into one interval, 0 to 2, integrated. Next interval, 2 to 3, and integrated. Okay, and 3, add the absolute values of the integrals. That's what we did last. So 7/3 was originally negative, but we took the absolute value, which made it positive, and added it to 16/3. We got 23/3. This is your summary of your steps, though. Example 7. Find the area of the region between the curve y equals x times cosine 2x and the x-axis over the interval -3 is less than or equal to x, which is less than or equal to positive 3. So we could do this analytically, but I'd like to do this one in the calculator just to show you how we would do this. So if I were to graph x times cosine 2x, we're looking at the window between -3 and 3. Okay, so you can see there's some areas where that is positive and some where it is negative. But when I'm integrating, I want all positive, okay? I don't want negative. And I don't want my total area to be decreased because of that negative. So what I'm going to do is go to Math, FINT, so number 9. And I'm going to do the absolute value of this graph. So I'm going to go back to Math, Number, and the first one here, ABS, means absolute value. So we're going to do the absolute value of x cosine 2x. And make sure you have 2 parentheses after that x to close out the absolute value, comma x, comma -3, comma 3, close parentheses, enter. Oh gosh, I messed up. Oh, I put in 2 commas where I should have only put 1. Okay, delete one of those. And thinking, you can do it. There we go. Okay, so calculator tells me that our area is 5.425 approximately. Okay. So 5.425. But to find this, remember you had to use the absolute value feature to actually get the total area, as opposed to if we hadn't done that. Let's see what we would have gotten without absolute value. Yeah, what did I do? I deleted the cosine. But we want to delete absolute value. Okay, so without that, you just get a 0, and you can see that that is a completely different answer. So absolute value is important here. And that is all that we're going to do for 5.4, Fundamental Theorem of Calculus.